Back in 1977, they detected a sequence, called it the wow signal.
What's it say?
You guys must have seen the series Three Body Problem, in which they detected a sequence in 1977 called a wow signal. So let us see how to detect and process the signal. So my name is Aryan, and the topic of my presentation is signal detection and signal processing of pulsar and FRBs. FRBs means fast radio bursts. So these are the table of content. So first we will see what are pulsar and how to detect them, and what algorithm or software we can use to detect them, and then at last a small introduction to FRBs, that is fast radio bursts. So introduction to pulsar. You guys might have heard about neutron stars, that they are massive stars with a strong magnetic fields. So pulsar are just a special case of neutron star. Like when a massive star explodes, it becomes into a neutron star. So in this image you can see a pulsar. They have a very high magnetic field. You can see a radiation beam from the poles. So these radiation beams radiate in the form of radio waves, and we can discuss some property of pulsar, like they have a very strong magnetic fields and they spin very fast. They are very precise clocks because they have extremely stable periods. So astronomers use these pulsar as precise clocks, and they are more precise than atomic clocks, so that's why we use them. So we are seeing here the pulse profile of a pulsar. So here we see a peak here. So pulsar can be thought of as a lighthouse which rotates, and it gives a beam at certain periods. So the pulsar also rotates and gives beam at certain periods. So this is the peak or beam we are getting after certain periods. So and now we have seen what are pulsars, so now we will discuss how to detect them. So you might think that finding pulsar would be very easy. Just point your radio telescope at a sky and look for the objects that blink, but it is not that easy because the signal has a very weak strength, and they are like background radio waves, or you can call them noise. These noise makes it hard to detect pulsar. To solve this problem, astronomers came up with a way called folding. So in the figure here, we have a signal in certain time period, and what we do is we fold these signals. We are folding the signal to get a main peak, or the main pulsar signal we are getting here. So as we fold them, the peaks are getting stronger and stronger, and we would finally be able to see our pulsar. But this method only works if we know the period of a pulsar, because we would have to fold these signals in a period. So we should know what is the period of a pulsar before doing this process. So like it is like a impossible task if we have a lot of data. So it will be impossible to analyze a lot of data using this folding technique. So we have to find some easy way. So Fourier transform is just a mathematical operation that converts time domain into frequency domain. When we Fourier transform a set of pulsar data, we can look for a signal in the frequency domain. If we find one, we can go back and fold our data in the time domain and determine if our signal came from a real pulsar. So we are just looking for signal in frequency domain, and if we find one, then we can go back in the time domain and determine the signal is coming from a real pulsar or not. So now we are detecting the pulsar. There are many things that may look like a pulsar, but they are not. So these things which may interfere with our main signal are the noise, and that is called radio frequency interference. That is the noise. So these are the man-made radio sources, like cell phone they emit radio waves, power lines they emit radio waves. So these noise makes it difficult for us to analyze the signal of the pulsar. To reduce this interference, radio telescopes are made away from the cities. Like you can see here, this is a green band telescope in West Virginia. So you can see the area surrounded by these telescopes. So as you may have begun to realize, there is a awful lot of work done on computers when it comes to finding pulsars. So we must find a certain algorithm or software that can ease our job. So Presto, it is a software used for finding pulsars. So Presto takes the Fourier transform data set and uses some clever algorithm to search for pulsar. So what it does is it transforms the data into frequency domain and then search for a promising candidate. And if it find one, and it can go back to the time domain data and use a program called prepfold to fold the data like we have seen before, and then we will get these plots, and these are called prepfold plots, and they will majorly give information about the signal we are getting. So these are different plots, so we will study each of them briefly. So we are going to discuss the first graph here. So it is a graph of time versus phase. So what does phase mean? A phase of 0.5 means the pulsar has gone through half a rotation. A phase of 1 means the pulsar has gone through one full rotation, and so on. So here you can see certain blocks. So there are three type of blocks here: dark, gray, and white. So darker the block is, the stronger the signal. The gray means less signal, and white means there is no signal. So here you can see this is the darker area, and here you can see the dark area. So this is the signal of a pulsar. So corresponding to these profile, you can see the peaks here. So darker the graph is, that means stronger the signal is. So these are the peaks we are getting here. So the next graph will be of frequency and phase. So at certain frequency, at certain phase, we are getting this signal here. So the signal is spread across the frequency, and all these chunks of frequencies are called subband. So we have our radio instrument. So what the instrument does is it break down the signal into small chunks of observing frequency. So each one of these chunks is called a subband. So a subband here, and these graphs can be used to determine the characteristics of pulsars. So now the most important graph, that is the dispersion measure versus reduced chi-square. So we will see what is a dispersion measure. So let us take example. We have a source here, and this is Earth. This is a source of radio waves, and this is Earth, and there is space between these two. So we know that space is majorly vacuum, but it is not true. It contains low density of electrons too. So there are electrons between the source and the Earth. So what the dispersion measure is, it is a measure of the electrons encountered by the signal. So the signal is coming from source to earth. So the electrons, the number of electrons encountered by, so the number of electrons encountered by this signal is the dispersion measure. The more the density of electrons, the more the dispersion measure. And if we increase the distance, then the number of electrons will increase between the source and the earth, so the dm will increase. So we have seen what a dm is. Now we will see what a reduced chi-square is. Reduced chi-square is nothing but a statistical value that indicate how well a model agrees with some actual data. The larger the value of reduced chi-square means that the model and the data are not in a good agreement. So we can use this reduced chi-square in a unique way. So we have two models. One contain pulsar and one doesn't contain any pulsar. It is pulsarless. So if we measure the reduced chi-square of the system, it will be higher because these models do not agree with each other. So if we see our graph at a certain dm, we are getting high reduced chi-square. This means that it is a signal of a pulsar. Dm of a signal is one of the best way we can distinguish between RFI, that is noise, and our real signal that we are seeing. So the next graph is of the period and period derivative. So this is the same graph. It gives us the same information. So this period out is nothing but it simply tells us how much the period is changing over time, and the period of a pulsar changes very, and the period of a pulsar changes very slowly. So these numbers are very small, and if we combine these two, then we will get this plot. This is nothing but a plot in 3D. So red area means high signal, and as it goes to purple, the signal reduces. So nothing but just a combination of these two plots. So now we are going to take an example. So this is the prep fold of certain data. So here we can see the graph of dm versus reduced chi-square. So here at dm is equal to 0, we are getting a peak. This means it can be a signal of a pulsar. So let us check. So what does dm is equal to 0 means? This is source, this is earth, and this is the space. So it means that there is no electron here, or the signal hasn't encountered any electrons. So in this case is only possible if the source and the earth, if the source is on the earth itself, which is noise. So this is not the data of pulsar, it is just noise. So the software we were using before was Presto, and these are the steps it takes to find a pulsar. You can see these steps. So the first pulsar was detected by Jocelyn Bell in 1967, and it was named as CP1919, and she was 24-year-old when she discovered the first pulsar. Now we are going to discuss or introduce fast radio burst. So you can see here the diagram, the flashes there that are blinking are FRBs in the universe. These are intense blasts of radio waves, and you can see how much energy they emit just in thousands of a second. So you can see how powerful they are. And we doesn't exactly know what causes FRBs, but the major Proposed candidates include magnetars, which are rapidly rotating neutron stars with powerful magnetic field. So these are the so, so this is still a topic of research, and research is going on in this topic. So thank you, and these are the resources used.